So the other factor is temperature. There's a reason why we run reactions. If you were in the lab, we run them at a certain temperature. We increase the temperature. It's because temperature increases the kinetic energy. So they move faster, they gain enough energy to overcome EA, which is again the activation energy. So all I'm going to say here to summarize all of this is by saying that you increase the temperature, you increase the kinetic energy, which increases the rate or the reaction rate of the reaction. Makes sense, makes them move faster, and they do. One quick thing to say about that is that EA values for most organic reactions are between 10 to 35 kcal per mole. When the activation energy is smaller than 20 kcal per mole, then the reaction goes readily at room temperature. I'm not asking you to memorize, but if I give you this information, you should be able to say, okay, well, at room temperature, the reaction should go readily. But if it's above 20, then I need what? Higher temperature. So what is room temperature? 25 degrees Celsius. Rule of thumb, this is very important in case I give you a multiple choice question or just for you to understand, is that increasing the temperature by 10 degrees doubles the reaction rate. So makes it move faster, but you have to be careful. You can't, again, raise your temperature to 500 degrees because you actually end up doing more damage by the reaction just becoming very hot, and too much kinetic energy ends up actually doing creating more side products, and you get virtually nothing. So you have to assess all of this before you begin your reaction. One other thing is that increasing the concentration also increases the rate of the reaction because it increases the number of collisions. So once again, if you have more molecules, that means you have a higher probability that they will collide in that given period of time, of course, with the right orientation. All of those comes together to kinetics and thermodynamics to put together what we call energy diagrams, which we did already. They're here, but we will now actually relate them to organic reactions. They're really, and I mean it, they're really straightforward. They may look fuzzy, but they're actually straightforward if you know your what delta H and delta G mean and EA mean. And of course, where your reaction products and reactants. An energy diagram is a schematic representation of the energy changes that take place as reactants are converted to products. And it indicates how readily a reaction proceeds, how many steps are involved, and how the energies of the reactants, products, and intermediates compare. So it tells you what's more stable, your reactants or your products, which tells you about their equilibrium, the equilibrium of the reaction, tells you how many steps. And of course, was it a fast reaction or was it a slow based on the activation energy? There's one thing we need to talk about is that the rate of the chemical reaction is determined by measuring the decrease in concentration of reactants over time. So think about it. You're making a product. After 1 hour, do you want to have the products or the reactants with the same concentration? So if I start with A and I have a concentration of 1 molar, and after 1 hour, I still have 1 molar. What does that tell you? Did it react? It's still A, no reaction. But if it goes now after 2 hours, goes down to half a mole, then you know that you're forming a product. So keep that in mind. A rate law or rate equation is an equation that shows the relationship between the rate of reaction and the concentration. So I will show you what I mean by that. And of course, the rate law is experimentally determined, and it depends on the mechanism of the reaction. So I'm saying a lot of words here, and I understand, but I'm about to show you actually in the next example. So if you look at this example, right here, you have a reaction going on. You have A, B, this compound, reacting with this anion, this nucleophile, and you form A as an anion and BC. So notice that there's something happening here. This is a one-step reaction, a concerted mechanism. So what happens is that AB reacts with C to form A minus and BC. And it was found that when you examine this reaction, that the concentration of both reactants affects or affected the rate. So what does that mean? This means only one thing, that if you double this rate, double the concentration, or let me just use words, that would be better. So if you double this, the rate doubles. And if you double this, also the rate doubles. And the rate law is the following. Rate is equal to K of AB, the concentration of AB, times the concentration of C minus. And think about it. If you double one of them, you double the reaction rate. If you double both of them, the rate, what do you think happens to the rate? It quadruples. Quadruples. So the rate depends, again, on the concentration of both. Now, this reaction right here is proportional to the concentration. It's called a second order because you have two reactants. That's why it's called a second order, and we call it a bimolecular. Bimolecular means we have two molecules at what we call the transition state. And the one last thing I want to say before I move on to the next one is that large rate constants K indicates that you have fast reactions. And what do you think small rate constants mean? You have slow reactions. So let's show you what happens here. Here's your reaction. Began with A and AB and C. The reaction took place. So these are my reactants right here. These are my products. What's important is what happens, what we call at the peak right here, that's called the transition state. And the transition state is basically what happened, again, in between. So think about this. Let's go back up here. Or let's actually write it down here. If we had AB plus C minus. Look at the transformation. Seems like C now is bonded to B and A is out. So this is the reaction mechanism. C formed a bond with B via this lone pair, and then A is no longer bonded to B, took its electrons with it. Remember those curved arrows. So meaning that as the bond between C and B was forming, the bond between A and B was breaking. And that right here is what we call the transition state. And this is how we draw it. Whatever is breaking, so here's A, here's B in the middle, and there's C. You put dotted line, which indicates that the bond between, let's say A in this case, is breaking as it was forming between B and C. And generally you put delta minus on here because again, this one is electron deficient. And again, it's bringing, C is bringing its electrons with it, A is taking its electrons with it. And you put that in, like I said, a double dagger like that. That shows the transition state. We'll talk about them when we meet on Thursday, how to draw them. They're not as bad as you might think. Now, how do we interpret this even better? Give more information. You know that this is a one-step mechanism, a concerted mechanism, because look at it. It just went from the reactants to the products right here in one step. There were no intermediates, because the intermediates would have to react with something to go to the next step or to the product. So this is a one step. It looks like a one hump and that's it. Told us that EA is a little bit high. And of course, what kind of reaction is this? Exothermic or endothermic? Right, so delta H is negative. So it's an exothermic reaction, which is, by the way, what we want all the time. We want exothermic reactions. So study this before we go on to the next one, because the next one is a two-step, and that would be the end.